Welcome, my friends. I'm so excited because in this video we get to talk about counting techniques. These are techniques that help us to count how many ways that different events can happen. So what are we waiting for? Let's go ahead and get started. The first counting technique to talk about is what is called the multiplication rule of counting. The multiplication rule of counting tells us that if there are A ways of doing one thing and B ways of doing another thing, then there are A times B ways of doing both things. And this idea could be expanded to more than 2 events. So if you had 3 or 4 events, basically if you want to find the number of ways there are to do all of those things together, you'd just be multiplying how many ways there were to do each of those things together. Let's look at an example. Let's say you have narrowed your search for kitchen appliances to the following choices. You are considering 3 different stoves, 5 different dishwashers, and 2 different refrigerators. How many ways are there to choose the 3 appliances? Or another way to think about this would be like, how many ways could you eventually have your kitchen look based on the stoves, dishwashers, and refrigerators? Well, you could have stove number 1, dishwasher number 1, and refrigerator number 1, or maybe stove number 1, dishwasher number 1, and refrigerator number 2, or stove number 2, dishwasher number 3. You can see there's going to be a whole lot of different possibilities for your choice of your appliances. So how many possible different ways could you choose your kitchen based on these choices? Well, based on the multiplication rule of counting, if there are 3 ways to do one thing, 5 ways to do another, and 2 ways to do a third, then the way to do all those things together would be to simply multiply all of those options together. So we have 3 times 5 times 20, which gives us 30 different options for our appliances. Sometimes you might want to repeat the same experiment over and over again and calculate the total number of outcomes. This would be another application of the multiplication rule of counting. Here's an example. Let's say we are flipping a coin 8 times. On each flip of the coin, there is 2 outcomes. So the first event is flipping the coin, either heads or tails. The second event is flipping the coin again, either heads or tails. And we really have this 8 different times. So we have 8 different events, and each event has 2 different outcomes. So altogether, we have 2 times 2, so that we have 8 2's, or that's the same thing as 2 to the 8th power, or 256 possible outcomes. One possible outcome would be flipping heads 8 times in a row. Another possible outcome would be 7 heads and then tails at the end, or any other combination of heads and tails together. If you listed them all out, there would be 256 possible outcomes. What about rolling a fair 6-sided die 3 times? Well, there are 6 different outcomes on each of the rolls of the die, and if we're going to be doing it 3 times, that's going to be 6 times 6 times 6, which is 6 to the 3rd power, or 216 different outcomes. One of those outcomes would be like a 6, a 3, and a 1. Or you could have a 1, a 3, and a 6. That would be a different outcome, right? Or a 2, a 4, and a 1, right? And if you listed them all out, you would have 216 different outcomes. So really, this is just the multiplication rule of counting, but it also applies when we have the same thing repeated over and over. Let's look at one more example. Drawing 4 cards from a deck of 52 cards, replacing each card and shuffling the deck before drawing the next card. Well, each draw of the card, there are 52 different options, and then since you're going to be placing that card back into the deck and then drawing again, each draw is going to have basically 52 different options. So that's going to be 52 times 52 times 52 times 52 for the 4 cards, or 52 to the 4th power, which comes to 7,311,616 possible outcomes. If you want to write this out kind of like a formula, in general, you might say that we have n to the r power to calculate one of these values, right? Where an event with n outcomes is repeated r times. Like we have the flip of the coin had 2 different outcomes, and we repeated that 8 times. So you would have 2 to the 8th power, or whatever for any of these other examples. Let's look at some additional examples. A password must contain 5 characters. The first character must be a letter, either upper or lowercase. And then characters 2 through 3 must be digits, and characters 4 through 5 can be any letter, upper or lowercase, or any digit, 0 through 9. How many possible passwords are there with these constraints? Well, you need to choose 5 different characters, so I would just kind of start out with 5 different blanks. And then the first blank is going to be a letter. It's going to be either a uppercase or lowercase letter. So there are 26 letters, and if we can be either upper or lowercase, and those are different, then we really have 52 different options. 26 times 2. And then we have the 2 digits, right? So we have characters 2 through 3 must be digits anywhere from 0 through 9. Well, there are 10 digits from 0 through 9. That's 10 different digits, so there are 10 options for each of those outcomes. And then the very last two characters can be any letter or any digit. And so there are 52 different letters, including upper and lowercase, and there are 10 digits. So altogether, there would be 62 outcomes for each of those two events. Based on the multiplication rule of counting, if there are 52 ways to do one thing, 10 ways to do another thing, etc., right, then there's going to be, multiplying all those numbers together to find the total number of possible outcomes, or in this case, the total number of possible passwords. And if you multiply all those together, you're going to get about 19,988,800 passwords. So quite a few. All right, here's one for you to try. A license plate in a state must contain 6 characters. The first 3 characters can be any letter except for Q or Z, and the letters are not case sensitive, so lowercase and uppercase would be the same. The last 3 characters can be any digit except for 0. How many possible license plates are there with these constraints? So do the same kind of thing here, list out all of your blanks, and then fill out how many options there are for each of those blanks based on kind of the constraints that we have here. And to find your final answer, you'll just be multiplying all those numbers together. All right, the next thing to talk about is factorial. So let's say that we have the 100-meter dash, which has 8 runners, and we want to know how many ways there are for the places 1 through 8 to be awarded. So really, this is just another case of the multiplication rule of counting. We've got 8 different places to assign, so we kind of have 8 different blanks. So how many possibilities are there for first place? Well, if there's 8 runners, then there's 8 possible people who could come in first place. So we're going to put an 8 in that first blank. But now if first place has already finished, then really what you have is 7 people competing for second place. So we're just going to put a 7 in the second blank. For third place, there's only going to be 6 runners remaining competing for third place once first and second have already finished. And we have that kind of continuing all the way down until we get to the 8th place. Once the 7 people have already finished, well, there's only 1 person left who is competing for 8th place. And based on the multiplication rule of counting, we can just multiply all those together to get the answer, which is 40,320. Now, there's actually a special name for this type of multiplication in mathematics. So if you start at some number and you start multiplying all the whole numbers until you get down to 1, this is what we call factorial. So this whole entire expression up here could be represented by 8 factorial, or 8 with an exclamation mark after it. Now, I will just note that your calculator can also calculate this factorial, so I want to show you that now, so you don't necessarily have to type all of this into your calculator. So if you have the TI-84 or 83 calculator, what you can do is you can type in the number that you want to take the factorial of. So that would be 8. You can press the math key, and then you can go over to the PRB for probability menu. I can scroll to the left to get there, and then choose option 4. And that's going to give me 8 factorial, which is the same number that we had here, 40,320. Now, in general, what is this number actually calculating? Well, it's calculating the number of ways to arrange that many objects. So in general, if we have n factorial, we say that n factorial represents the number of ways to arrange n objects, or in our case, 8 objects. And this is a very important definition that you're going to want to make sure that you have memorized. Anything factorial is just saying, well, how many different ways can you kind of mix and match 8 things? Or in this case, how many ways could you have those 8 runners finish the race, right? Now, for certain formulas, you might need to use either 0 factorial or 1 factorial. And just know that those are both defined as equaling 1. All right, the next thing to talk about is permutations. So let's look at a slightly modified example. How many ways are there to award first, second, and third place to the 8 runners in the 100-meter dash? So this is kind of a slightly modified version of the previous question where we asked how many ways there were for all 8 people to finish the race. But now we're only concerned about the first 3 finishers. So it's very similar, but we will only have 3 blanks this time, right? First place, second place, and third place. So how many ways are there to award first place? Well, there's 8. There's 8 different people who are competing for first place. And once first place has been awarded, there are 7 people remaining competing for second place, and then 6 people remaining for third place. So based on the multiplication rule of counting, we have 8 times 7 times 6, or 336 different ways to award these 3 places. So this is the same thing as 8 factorial, but we are stopping early. We still have that idea that we are, multiplying down the numbers, but we are not going all the way down to 1. And this is what we call a permutation. A permutation is just basically a factorial that terminates early. Now, you can use the permutation to count the number of ways that something can happen if you have the following two conditions met. So first of all, you must be sampling without replacement. Really, all that means in this example is, once someone has finished the race, they can't, also take another place. Like someone can't be both in first place and second place. So once that, first person finishes, he can't also finish in another place, right? So that would be the sampling without replacement requirement applied to this example. The second condition is that the order or arrangement that the objects are chosen does matter. And all that means is, one person coming in first place versus second place is a different outcome than if you mix them around, right? So if you've got, Max is in first place and you have, John in second place, that's different than if John was in first place and Max was in second place. In certain circumstances, switching those around might not actually make a difference. We'll look at examples of that in just a minute. But to use a permutation, we kind of have to have the condition that the order those objects are chosen does matter, right? So as long as we have met those two conditions, we can use this idea of a permutation. Now, I will just note that there is a key on your calculator to calculate this as well. So if we go to the calculator here, the way you need to do this is you need to type in kind of your starting number first, which in this case is 8. We can press the math key, and then we can go over to the PRB menu. And this is the second option down, NPR. And then you'll put in the, basically how many options you're choosing here. There are 3 different places to award. So you put a 3 there, and you will see you get the same answer as 8 times 7 times 6. Okay, so permutations are very similar to another type of counting technique, which we call the combination. And a combination is the same thing, except for well, first of all, we're still going to have that first condition of sampling without replacement, but the difference is now the order that the objects are chosen does not matter. So now if you kind of like rearrange the objects once you've chosen them, if it doesn't really make any difference or is not significant, then you would be using what is called a combination. So let me give you an example of that. So maybe we were asked how many ways there are to choose 3 friends to invite to a party out of 10 total friends. So you got 10 different friends and you're going to have a small party and you want to know how many ways could I possibly choose 3 of those friends. And if we stop to think about this, the order that I choose those friends doesn't really make any difference, right? If I choose to invite Max first and then invite John second, that's the same thing as inviting John first and then Max second. Like either way, I'm still inviting the same people to the party. So now actually we're not going to have quite as many, I guess, options you might think as when we had the permutation, because now we don't really care about the order that these objects are chosen or invited in this case, right? So the way you think about this is still using the same kind of idea as different blanks here. That would be kind of the starting point. You'd say, okay, I've got my first friend, my second friend, and the third friend. I've got 10 options for the first friend. Once I've chosen that person, well, I can't choose him again. I've already invited him. I don't have a replacement. Then I have 9 friends remaining to choose for the second one to invite, and then 8 for the third, and that would give us 720. But this number is too high. This would be the permutation, right? This would say that inviting those friends in a different order is going to be a different outcome. But that's not true, right? Ordering the friends. Inviting the friends, but in a different order is not actually going to be a different outcome, right? So we have to somehow kind of adjust this number. So how do we have to adjust this number? Well, recall that any number factorial just tells us how many ways there are to reorder that many objects. So if in this case we have 3 different friends, how many ways could you reorder those friends once you have, already invited them? Well, there would be 3 factorial ways, or 3 times 2 times 1 equals 6 different ways to reorder those 3 objects or friends. So that's kind of the factor that we have to adjust this number by to kind of get rid of the order, right? So the way we end up doing this is we take that number and we divide it by how many ways there are to reorder those 3 things, or in this case, those 3 friends, which ends up being 120. So all things together, we would say that there's 120 different ways to choose 3 friends to invite to a party out of 10 total friends. Now you can also calculate the combination on your calculator in a very similar way. So let me kind of move this up a little bit. So just like with the permutation, you should type in your, how many objects you have first, which in this case is 10. And then we can press the math key, arrow over to the PRB menu, and then choose the third option down for NCR. And then we would put in how many objects we're choosing, which in this case is the 3 friends, and you will see that we get 120. All right, so let's go ahead and summarize some of the things we've talked about, including some of the notation. So we've already seen some of this notation in the calculator, but with respect to permutations and combinations, n is going to represent the total number of objects, like the 8 runners in the race, or maybe like the 10 friends, and r is going to represent the number of objects that you are choosing. And the notation that we saw in the calculator here was we have either NPR or NCR for the permutation or combination. And the way you would read this is the permutation of N choose R or the combination of N choose R. N will always be a bigger number than R because you have like a group of objects that you're choosing from, and R would be how many you are choosing. So if it was like 8 and 3, you would say the permutation of 8 choose 3. Or if it was like 10 and 3 like we had with the friends, it would be the combination of 10 choose 3. If you want to calculate these things for the permutation, you're basically doing a factorial idea where you stop early, right? So you're doing n times n minus 1 times n minus 2, and you'll continue to do this until you have r numbers, right? When we had r is equal to 3, we had 3 different blanks that we were filling in. If you want to find the combination, then you're simply doing the permutation, but you need to adjust so that you are not accounting for the order, right? Since the combination does not include the order or the rearrangements of the items, you need to kind of adjust for that by dividing by r factorial, the number of ways there are to rearrange those r objects. Now I will mention there are different formulas that you might see online to calculate permutations and combinations, but I'm going to opt to use these ones in this class because I think they're a little bit simpler and easier to understand. Let's look at some additional examples. So let's say we are asked how many ways there are to choose and rearrange 4 pictures on a wall from 12 total pictures. So that means that n, our total number of objects, is going to be 12, and we're going to be choosing and rearranging 4 of those pictures. So the question is, are we going to use a permutation or a combination? And the question we need to ask ourselves is, does the order in which these objects are chosen matter, or does it not matter? Well, in this case, if we could rearrange the pictures and get like a different outcome, then that is kind of telling us that the order does matter, right? If I put picture number 1 first and picture number 2 second, or if I switch them around, I would consider that to be like a different outcome, right? Because now the pictures are in a different location on the wall, and therefore that's going to be like a different outcome, right? So that means we're going to be using a permutation, the permutation of 12 choose 4. And the way to calculate a permutation is do the factorial idea, starting with the number on the left, and only so that you have 4 different numbers, right? So you're going to have 12 times 11 times 10 times 9. So this is 4 different values, which if you multiply that out is 11,880. How many ways are there to make a 5-ingredient pizza from 11 possible ingredients? Well, the total number of ingredients is 11, so n is 11, and we're going to be choosing 5 of those ingredients for the pizza, right? Now, in this case, the order does not matter, right? It doesn't matter what order I choose those pizza ingredients, presumably, right? It doesn't matter if I put the onions on first and then the mushrooms, or vice versa. Most likely, that probably doesn't make a difference in terms of the pizza. They're all just ingredients on the pizza, right? So we would say that the order that you choose those ingredients does not matter. So therefore, we would be using a combination. And to do a combination, you're first going to find the permutation, and then you're going to divide by r factorial. Because once you've chosen those 5 ingredients, you don't care about the reordering of those 5 ingredients. So we divide by 5 factorial to kind of get rid of the order. So the permutation of 11 choose 5 is 11 times 10 times 9 times 8 times 7. That's 5 numbers here, divided by 5 factorial. If you multiply that out, you should get this result, which eventually simplifies down to 462 ways. There's 462 basically pizzas you can make if you have 11 ingredients, and you're going to be choosing 5 of those ingredients. All right, so here are a few additional examples that we are going to look at here. So first we have a computer password, which must include 5 letters, where the letters are not case sensitive, and the letters cannot be repeated. How many passwords are possible? Well, saying that the letters cannot be repeated kind of gets us that first condition for permutations or combinations, right? We had to have no repetition or no replacement, right? So we have 26 possible letters since they are not case sensitive, and we're going to be choosing 5 letters. Does the order matter in which those letters are chosen? Well, yes, the order does matter, right? If my password was ABCDE, that's different than EDCBA. Even though I have the same 5 letters, ordering them, differently is going to create different passwords. So I'm going to be finding a permutation. So it's the permutation of 26 choose 5, which is 26 times 25 times 24 times 23 times 22. I've got 5 different values here, and that comes to 7,893,600 different passwords. Here's another example. A committee consisting of 4 faculty members and 5 students is to be formed. Every committee position has the same duties and voting rights. There are 7 faculty members and 8 students eligible to serve on the committee. In how many ways can the committee be formed? Now this one is a little bit trickier because actually you have kind of 2 different things going on here. You need to select some faculty members for this committee, and you also need to select some students for the committee, right? So you kind of have to think about those 2 things separately. But either way, the order that you choose those individuals is not going to make any difference, right? Since every committee position has the same duties and voting rights, it doesn't matter if I choose, Julie first and then Sam second, or Sam first, then Julie second. They're all just going to be part of the committee or not part of the committee, right? So there's not really any difference between the individuals. So that is kind of what we mean by order in this context. If each committee person had like a different duty and they had special roles, then we would be using a permutation. But in this case, we say the order does not matter. They're all kind of the same position. So we need to separately think about the faculty members and the students. So there are a total of 7 faculty members to basically choose from. So that's an n equals 7. And there are 4 faculty members that need to be on this committee. So R is going to be 4. So this will be the combination of 7 choose 4, which I've not written all the work here, but that will end up being 35. And we also have to choose the students. So there are a total of 8 different students, and we're going to be choosing 5 of those for the committee. So that's the combination of 8 choose 5, which is 56. So how would we find the total? Well, this is another idea of the multiplication rule of counting, right? So we have a committee which is going to have faculty members, and there's 35 ways to choose the faculty members, and there's 56 ways to choose the students. So in total, there's 35 times 56 ways to choose both of those things. So that comes out to 1,960 different ways you could choose this committee. All right, so here are a couple of examples for you to try out. So go ahead and pause the video and work through these, and then in a minute, I'll be back to work through the first and the third answers. All right, so hopefully you've given those a shot. The first one says a troupe of 8 dancers is going to line up on stage. Of these dancers, 4 are wearing black and 4 are wearing red. A dancer wearing black must be in the first position, and the dancers must alternate between colors. In how many ways can the dancers line up? So I'm going to opt to view this one as a multiplication rule, right? So we have 4 people wearing black and 4 are wearing red, and they're kind of alternating. This isn't really going to work for permutations or combinations. We really have to think of this as a multiplication rule type problem. And first we have to choose a dancer wearing black. They must be in the first position. And then after that, we're going to be alternating between the colors. So the second person has to be red, and there's 4 people wearing red. And then we'd have to go back to black. And since we've already chosen one person who's wearing black, we'd have to have only 3 options here, and then red, and then black, and then red, and then black, and then red. And if you multiply all those together, you get a total of 576 different ways that you could choose to kind of set up these different dancers. I'm going to skip number 2 here, so I'll give you a chance to try that one out on your own and think about what counting technique is being used there. And we have the last one here, which is in the Cash Now lottery. There's 10 finalist tickets. From those tickets, 3 prizes are going to be drawn. One's going to win $1 million, one's going to win second place, and one's going to win third place with different prize money. How many ways are there for those winners to draw, assuming the same ticket cannot win twice? So in this case, the order is going to matter, right? Because if I choose one person to win $1 million and a different person to win 100,000, switching those around would be a different outcome. So therefore, the order does matter, and I do not have replacement I don't have replacement because the same ticket can't win twice. So this is going to be a permutation. It's going to be the permutation of 10 choose 3, since there's 3 different kind of outcomes here. So that is going to be 10 times 9 times 8, which is going to be 720. There's 720 different ways to award those 3 prizes. All right, I think that finishes everything I wanted to talk about related to counting techniques. So hopefully you found that useful, and I will see you again in the next video.